So, the lecture 2 will be in detail about the MOSFET device. So, we will not basically discuss too many things about this here, but MOSFET as a transistor will come in two different forms. One is called N-type MOSFET, in short NMOS. The other one is called P-type MOSFET, in short is called PMOS. So if we compare with BJT, BJT also comes with two forms, NPN and PNP. MOSFET also comes with a two different structure. One is called NMOS, one is called PMOS. This one is NMOS, where source and drain are made of N-type transistor, and the body of the terminal that hold the transistor that holds the source and drain region is called the body or the bulk silicon, that is P-type. On a P-type body, if source and drains are N-type, we call it NMOS transistor. On an N-type body, if source and drains are P-type, then we call it PMOS transistor. Gate is a conducting layer. At the initial stage of MOSFET technology, it was made of metal. That's why the name metal oxide semiconductor. But now, in the current process, we no longer use metal, but a polymer of semiconductor, which gives us a property, behavior like a metal, a conductor. So, right now, in the current process, we use polycrystalline silicon, or polysilicon, that actually is a conductor and it behaves like a metal. And silicon dioxide is still the main insulator used across the different IC families. In some very rare ICs, we use other insulation material, and the base material is still silicon. And this one is a symbol of NMOS transistor. This one is a symbol of PMOS transistor. The difference is there is a bubble, circle at the gate terminal. We will explain the difference, but if you look at any of these two signals, what do you see? This line represents the gate layer. This is gate terminal. This line, this structure represents the body. One will be source terminal, one will be the drain terminal. Between the gate layer and the body of the transistor, there is a vacuum, there is no connection. That represents electrically they are isolated. Because of the presence of this silicon dioxide layer, electrically the entire body of the transistor is electrically isolated from this gate layer. So this not having any connection, or this gap between gate layer and the body part, represents that insulation, electrical isolation. For same NMOS and PMOS. If you remember, in logic algebra or in logic circuit, when at the terminal of any logic connection, if there is a circle or bubble, it means it's a negation, inversion. That means this transistor will be turned on when you apply a positive or high voltage. This transistor will be turned on, this symbol, this dot or circle, it indicates that this will be turned on when a negative or low voltage will be applied to this transistor. So NMOS can be turned on with a high or positive voltage. PMOS can be turned on by applying a negative or low voltage. So that symbol indicates. So if you see a symbol of an MOSFET with this, you immediately know it's a PMOS transistor, and you need a negative voltage or low voltage to turn it on. NMOS will be the other way. Now the question is, we explained it a little bit, but let's elaborate it more. Technology selection for integrated circuit. Why MOSFET has become the dominant technology for all integrated circuit? So, like in early 60s, BJT replaced vacuum tubes overnight. Gradually, from 70s to 90s, in 3 decades, MOSFET largely replaced BJT in most of the IC technology. Number one, the quiescent power required by the base of the BJT will limit its integration density, will limit its energy efficiency, so we cannot put them close to each other. It will generate some heat, significantly more than MOSFET. So the power consumption, which was the main reason, and the resulting heat, while BJP was replaced, and for the same reason BJP was replaced by MOSFET. Initially BJT replaced vacuum tube, now BJT is replaced by MOSFET for the same reason. As we explained, because of the insulation between gate and the body of the transistor, ideally to turn on a MOSFET, you don't need to inject any power. You just need to apply an electrical field because it's a field action transistor, field effect transistor. So ideally it consumes zero current at the input terminal to turn it on and off. So this lower power consumption allows very high integration, so you can put more transistor per chip. As a consequence of its field effect action, and its ability to be turned on at ideally zero or very, very small voltage, its speed and noise tolerance will be significantly higher because gate is separated or insulated from the body. So there will be no noise injection from the gate to the body. In case of BJT, the base is connected electrically to the emitter and collector, so there will be higher noise injection in BJT. So MOSFET will be more reliable, will provide much higher gain, and which will provide much higher integration density. So that's why MOSFET has become the dominant sort technology platform for all the ICs. When in early 70s, when Intel introduced the first commercial version of microprocessor and the first commercial version of RAM chips, initially all the IC companies, including Intel, didn't have the ability to integrate NMOS and PMOS transistor on the same chip. They had to rely on all NMOS transistor or all PMOS transistor. So that's why earlier generations of MOSFET-based IC technology, they were known as NMOS only process or PMOS only process. That means on the same semiconductor chip, they could not integrate two different types of transistor due to process complexity. So initial generations of MOSFET ICs contained only all NMOS transistor or all PMOS transistor. So thereby they were known as PMOS only technology or NMOS only technology. The question is then why we needed to integrate NMOS and PMOS transistor on the same chip. But before answering the question why, but let's introduce the third type of MOSFET technology. It's called complementary MOSFET technology, in short, CMOS. Current digital IC is almost 80 to 90% based on CMOS technology. What is CMOS technology? If an integrated circuit is implemented by using both NMOS and PMOS type of transistor on the same chip, we call it complementary CMOS, complementary MOSFET technology, that means CMOS. So, MOSFET technology can be of three types. NMOS only, PMOS only, and CMOS. CMOS is the integrated circuit based on MOSFET technology where NMOS and PMOS transistor will be used together to implement any logic circuit. NMOS only is the MOSFET technology where all logic circuit will be implemented using NMOS transistors only. PMOS only technology will be the integrated circuit where all the integrated circuit, logic circuit will be implemented only by PMOS transistor. Now the question is why PMOS became the dominant technological platform for all digital ICs. Now even some analog and mixed signal ICs are being implemented by CMOS technology. Why is that? Later in lecture 2 you will find that. But let's go back a little bit. How do you define a digital circuit? Digital circuit is any electrical circuit, they process electrical signal, right? A digital circuit handles only two types of signal, ones and zeros, high or low, true or false. You can call it in many different names, right? So digital circuit signals, it can be 1 or 0. Let me write it this way. So digital signal classification, depending on which literature you are following, 1, 0. Sometimes it is also known as high or low. But actually from electrical circuit point of view, what 1 represents? It represents a charge or a voltage equivalent to VDD or supply. It represents a charge or voltage equivalent to ground potential. So if the output of the logic circuit is equivalent to VDD, we call it logic 1 or high, and there is another name. We call it true or we call it false, right? It's same thing. But electrically, a binary 1 signal, a high signal or true signal is nothing but a voltage or charge equivalent to the supply of VDD. This is nothing but a voltage or charge at the output equivalent to ground. So a digital logic circuit or any digital electronic circuit can have only two electronic state, 1 or 0, VDD or ground. That's why we call it binary circuit. So another name of digital logic circuit is binary circuit because it can only have two possible electrical state. So to implement any logic circuit, including typing any anything, like even if you are typing A is what? It's a series of 8 binary bits, ones and zeros in a certain manner. So every byte is 8 bit. Letter A is nothing but 8 binary signals. It's a combination of ones and zeros. So a logic circuit must have the ability to produce 1 and 0, high and low, whenever needed. If any logic circuit can only produce 1, that is a useless logic circuit. That is not a logic circuit anymore. Because for it to be considered as a logic circuit, it has to operate like a binary circuit. So you will see that out of these two types of MOSFET transistor, NMOS is very good at producing perfect ground level or low signal. But it cannot produce perfect high or 1 signal. On the other hand, PMOS is very good at perfect strong high signal or binary 1 signal, but it is not very good at producing low signal. So in CMOS circuit, we want to utilize best of the both. We want to utilize NMOS for producing ground or 0 potential or binary 0 signal. We want to utilize PMOS for producing binary 1 or high signal. That's why CMOS circuit is significantly more robust than any other circuit, including NMOS only and PMOS only. Yes?
I have a question, like if NMOS and PMOS were in 1970s, if the NMOS and PMOS implicated in every chipset, how they get if NMOS cannot produce 0,
very good question. I know what you are asking. That's why they could get away with it. At that time, microprocessors were running at less than 10 megahertz, right? So it was not even at the hundreds of megahertz. It's like less than 10 megahertz. So the circuits were very sparse, voltage were very high. So all those small distortion compared to supply level, it didn't come as a big distortion. So NMOS, since you asked, NMOS will produce a perfect ground or low signal, but NMOS will produce a slightly distorted high signal. So it will be not exactly equal to VDD, it will be slightly below VDD. But if your VDD is 5 volt, a 0.1 volt distortion is 1/50 distortion, right? But if your supply now is 1 volt, a 0.1 volt distortion is like 10% distortion.
Yes.
So the signal with the slightest noise, signal can flip. So at the initial version of Intel and other microprocessors and memory chips, supply were very high in the 5 to 10 volts, and there were a very limited number of transistors compared to current days transistor, so they could be placed much further away, so the noise was less.
God.
And that 1 volt distortion compared to 10 volt supply was insignificant compared to now we are operating some of the Intel processor at only 0.9 volt. So 0.9 volt supply, if you have a 0.1 volt distortion for an NMOS, then it's a huge distortion. So it's a relatively, circuits have become more vulnerable to noise because of the overall reduction of supply. As a consequence, now we cannot use NMOS only. But earlier versions, yes, but still they had some distortion.
And the reason why, like for example, NMOS can't produce a good high level is because of the voltage drop across the.
We will have actually 7 to 8 slides on that.
Okay.
It's a very, very important concept. You have to learn to design CMOS circuit. Okay. So now let's talk about CMOS. So we have been basically laying the groundwork to start talking about CMOS. So the CMOS, the concept was given by a scientist, Mr. Frank Wanless of Fairchild Semiconductor. It was his bad luck that in electrical engineering didn't have Nobel Prize. It was a 2-page paper. He gave this concept. 10 years after that, he completely revolutionized entire microelectronics with this invention. So the concept was given by him in 1963, but initially with BJT, the MOSFET technology was not pioneered at that time, so it was just a conceptual design, but he gave that idea that two complementary type of logic device can be put together in the same circuit to produce binary high and binary low at the perfect strong level. So that is basically his concept. Later was implemented in early 70s by Intel and other companies. So that was the beginning of CMOS, the idea of using two different complementary types of logic device. One will be responsible for producing one will be responsible for producing 0. That's why they are complementary in terms of function. So the idea is inside the logic circuit, there will be two groups of transistor. One will be responsible for producing high signal or one signal. One will be responsible for producing low signal or binary 0 signal. So this block's function is to produce 1. This block's function is to produce
Low.
0. But all the transistor in this block will be one type. All the transistor in this block will be another type, different type. In this block, we will have only one type of transistor. In this block, we will have opposite type of transistor, all the same. So they are complementary to each other in terms of function. They are complementary to each other in terms of construction. What type of transistor we are using to build them. So that's called CMOS circuit, complementary MOSFET circuit. A circuit made of two complementary blocks of transistor. Each block will contain one specific type of transistor. Each block is responsible for producing one specific type of binary signal, 1 or 0. So during the early stage of IC technologies, from BJT to MOSFET, it took about 12 years to make the transition. in between, Motorola, Fairchild, and many other companies, they came up with many different types of IC logic design style. Quickly, I will show you a few examples. We are not going to basically spend that. This is called emitter couple technology, still based on CMOS, so it's still based on BJT, slightly different from TTL logic implemented by Texas Instruments, and it was pioneered by Motorola in 1966. Now, this is what actually the historical figure of 3 generations of Intel microprocessor and memory chip. First 4 kilobits of memory using MOSFET was introduced by Intel in 1970. And then Intel first microprocessor 4004 4-bit microprocessor came into market in 1972. At that time, these were all NMOS only process. PMOS, they couldn't figure out what to do with PMOS, but they can only use NMOS. So, this is Intel Core 1001 256-bit SRAM. This is the first microprocessor. And then in 2003, microprocessor technology took a huge jump in terms of its ability and processing power and circuit density. Up until then, we used to call it 286, 386, 486, right? So the very first PC I saw when I was in 9th grade, so that was the 486, right? At that time, the price was about $3,000. So one computer, 10 students were like sitting behind our teacher. We were not allowed to touch the computer because the whole school had only one computer. So, and it was a 12-inch black and white monitor. So, but this 486, and then around Intel, they wanted to introduce another 586, but for 5 to 7 years, they didn't introduce anything. At that time, they were like doing this. So, two crazy guys, his name is Mustafiz, not our Mustafiz Rahman, Mustafiz, and the other one is Anirudh. One guy from Buet, Bangladesh, and one guy from IIT India. Both of them were senior scientists at Intel R&D. They introduced a new structure for Intel microprocessor. Both of them are in Intel Hall of Fame. Later, Mustafiz went out. He started his own company, which was later bought by Intel's competitor, and there was a huge lawsuit. And Anirudh, he went his own way. He started another startup. This structure was given by those engineers, and they revolutionized the microprocessor technology in 2003. And that microprocessor, they started a new naming. They abandoned 286, 386, 586, or 486. They called it Pentium 4 microprocessor. And that processor contained 55 million transistors below 150 nanometer technology, or 0.15 micrometer technology. And then later, Intel introduced 512 megabits dynamic memory DRAM that contained 500 million transistors. I'm not sure whether it's Intel or Micron, one of the memory company, but the first 500 megabits of DRAM, it contained 500 million transistors. So it actually shows why I put this side by side. Here you have the number of transistors in thousands. Here hundreds of thousands. Here in millions. And as you can see, side by side comparison, the chip size almost same. So what enabled to go from here to here in exactly 33 years? The only thing that enabled us to do that is to make this device smaller and smaller. Now I am going to introduce a very, very important, the most important definition, that is called definition of technology. Some of you already probably know. So, those of you who know, don't raise your hand. Anybody, okay, now anybody can read. What do you mean by if I say this, the microprocessor in this phone? I have a very unsmart phone, 7 years old. So, microprocessor in this phone is based on 50 nanometer technology. What does it mean in this diagram? The microprocessor in your laptop is, let's say, 75 nanometer technology. What does it mean in this? And then I will explain the relation with the technology definition, size, and that chip size.
Is that the width of the transistor?
Width of the transistor, length of the transistor.
Okay.
One of the dimensions. Which dimension? Anybody can add. Those who knows can now jump in. What dimension we are talking about when it says 50 nanometer technology?
Is it the width of the gate?
Length of the gate, exactly. The length of the gate or the separation distance between source region and the drain region. As you can see, vertically they align. So the length of the gate, ideally, the actual definition is the distance between source and the drain. But ideally, gate length should be exactly equal to this distance. So technology size is the distance between source to drain, and this is called channel. The channel of the transistor from source to the drain. The channel length ideally should be exactly equal to the width of the insulation layer, should be exactly equal to the width of the gate. But there is nothing ideal. There will be some distortion. But the channel length is the technology size. What is the channel? The distance between source and the drain. So the technologies, if anybody says it's a 50 nanometer, that means length of this channel is 50 nanometer, length of this silicon dioxide layer should be 50 nanometer, length of this gate should be 50 nanometer. But these two will hardly follow this, there will be some distortion, but the definition is determined by the distance between source to drain. If it is 50 nanometer, we call it 50 nanometer technology. Now, let us introduce a related definition. It's called technology scaling. So, technology definition and technology scaling. Technology scaling, so means basically we have introduced the definition itself. Technology size, that is length of the channel, and the channel is the distance between source and the drain. And the next terminology we are going to introduce, technology scaling. What is technology scaling? Technology scaling means sizing down the transistor. Scaling down the dimension of the transistor is known as technology scaling. So we started with 10 micrometer technology in 60s. 10 micrometer means 10,000 nanometer. 1 micrometer is 1000 nanometer. So 10 micrometer is 10,000 nanometer. Today we are talking about 18 nanometer in Intel Core 7 microprocessor. So from 10,000 nanometer continuously we sized it down to this is now only 18 nanometer. So if we bring this to closer and closer, that means all other dimensions of the transistor must be reduced proportionately. That's how we were able to, by technology scaling, we were able to cram so many transistors, 55 million, and then of course half a billion in DRAM on the same side of semiconductor chip. Technology scaling that actually enabled us to cram so many transistors. So now from 60s to up until today, but this slide was prepared based on up until when Pentium 4 processor was introduced. In that time frame, from 58 to 2003, IC industry experienced a 53% growth annually. That means the number of transistors that can be integrated, could be integrated per unit area of the IC increased by 53% every year. That means efficiency and the speed and functionality of ICs increased 53% every year continuously for 45 years. So no other technology or no other industry could mimic even a fraction of the growth that was experienced by IC industry. That's why our life has changed. In my own lifetime, I have seen, first in my elementary and middle school, I did not see a PC. In my high school, I saw a PC which had only a hard drive. And then later in my high school, I saw a PC with a 5-inch floppy drive with a capacity of 50 megabytes. And then early in my college days, I saw a 3.5-inch floppy drive with 100 megabyte capacity. At that time, in my college days, we used to have a small plastic or metallic box with 10 of those, maximum 5 to 10 of those floppy drives, 3.5 inch. If you had one of those, then you are one of the either geek or coolest guy in the class, right? So, and then now you probably have never seen floppy drive. Now you have sometime Intel introduced the USB drive. You have flash from regular USB to 3C, 2C. Now you have current generation. There is nothing to plug in, no flash time. Everything is on the cloud, right? So it's so rapidly growing. Now, the person who first predicted that IC industry or microelectronics or nanoelectronics will experience this level of growth was no one other than Mr. Gordon Moore. So his prediction of 1965 became known as the Moore's Law, which is the guiding path for IC industry. Moore's Law is not a law of physics, it's just a prediction. Rumor has it, he was fishing on his yacht in a small island in the coast of California. And all of a sudden, this idea, this observation, based on his understanding of IC industry, by the way, he's the founder of Intel. So his understanding was much better than any of us. So based on his understanding of IC technology and industry, he predicted that the number of transistors that can be integrated inside the chip, that capability will increase by a factor of 2, double at every 18 months. And this observation has become known as Moore's Law. So if I just want to give you a simple funny information, in 2003, entire semiconductor industry globally produced enough IC. If you add them together, that will be equal to 1 quintillion of transistor, 10 to the power 80. It looks like a small number. But if you divide that number by the population, or global population of 2003, IC industry produced 100 million transistors for every human being on the planet. Now probably it's several billion or more. So the question is how we were able to integrate so many different transistors. The answer is again using technology scaling technique, technology scaling of technology size, by continuously sizing down the transistor. So during this time, not only the ability to integrate more and more transistors increased, during that time, clock frequency or the speed, clock frequency and the speed, these are interchangeable terms when it comes to IC. So clock frequency or electrical circuit, clock frequency or the speed of integrated circuit also increased to an unprecedented level over these few decades. So this is a actual progress of Intel microprocessor from initial 4004 to Pentium 4, from 1970 to 2003. And this plot tells us the number of transistors over the year and over the generation of Intel microprocessor. It reveals that number of transistors in Intel microprocessor doubled every 26 months. Moore predicted that every 18 months. But it was not a law of physics. But Intel could actually double every 18 months, but Intel didn't do it because when they sent out a microprocessor to the market, they needed some time to amortize the capture the capital back before you send another product, right? So they had to kind of stage it for many other factors. And then during this time, speed or the clock frequency of Intel microprocessor doubled every 34 months. Another interesting observation. After 2003 and 4, Intel and all the IC companies decided to give up on increasing signal microprocessor frequency anymore. They thought about 3 gigahertz, 4 gigahertz microprocessor of individual microprocessor, but later we will see that by increasing microprocessor speed, you have to sacrifice tremendously on energy efficiency. You want to run this cell phone or tablet, or your laptop is not hooked up with any power connection. So you want to run your laptop or the cell phone much longer for a smaller amount of charge stored here, right? That means energy efficiency is as important as the speed. But the problem is, if you want higher speed, you have to sacrifice energy efficiency. If you want higher energy efficiency, you have to sacrifice speed. So Intel and all the IC companies realize that if we try to unilaterally increase speed, the energy consumption will go to a such level that it will melt the IC. So they had to stop increasing clock speed further. But the question is, you still need to do more functions. You will still want more apps, more files to be handled, more different types of applications to be handled by your microprocessor. That means throughput or the work output of every microprocessing system, every electronic device must increase from generation to generation. How they did that? By splitting the microprocessor into smaller core. Each core will be running at a much smaller speed. Like instead of 1 worker, let's employ 2 worker, 4 worker, 8 worker, dual core, quad core, 8 core, 16 core microprocessor. So each one of them will be running at maximum 2 gigahertz. But when you employ 4 of them, 8 of them in parallel, together, overall microprocessor will give you much larger amount of function or work output. So that's why at one point they decided to, well, let's not try to increase individual core frequency anymore. So another interesting observation, many of you probably were not born, the semiconductor market share from 90s continuously started growing. And year 2000, at the transition of 1999, year 2000, all on a sudden, sale of electronics product, computing products increased exponentially, and then it became saturated again. Anybody have any idea why it increased semiconductor market at the transition from 99 to 2000? Anybody? Anyone of you heard about Y2K bug?
Is it the internet?
No, originally in the microprocessor signal, the date format, they used 2 digit for day, 2 digit for month, 2 digit for year. So at midnight 2000, 0000, all zeros. So they thought that because before midnight it was 12:31. Right at the midnight it is 000 because year 2000 last 2 digit is 0, right? So they thought that all digital system will collapse because it will not know how to calculate the clock frequency, because clock frequency has to be calculated with respect to a clock. If that clock sees all zeros at midnight, that means all function computing will collapse. So everybody wanted to upgrade a newer version of computer, but then later realized that all it needed a simple operating system level tweaking just to change the OS, because there was no physically hardware clock with 2 digits. All you needed an operating system level changing from for a year, just assign 4 digits.
If I recall correctly, the only device that ended up actually failing was one single vending machine in I want to say in Scotland or something.
Yeah, because probably the operating system couldn't figure out what to do. So, and then it started again going slowly upward. So now let us talk about this. We already explained transistor size. That is the technology size. That is the definition of technology. In 1971, 4004 microprocessor used, as I mentioned, 10 micrometer, that is 10,000 nanometer, and continuously scaling down. By 2003, Pentium 4 processor, it used 130 nanometer, that is 0.13 micrometer transistor technology, and that was the beginning of nanometer design. Now, when we move to fraction of a micrometer, we are in nanometer range. So that was kind of, now everything is in nanometer. We are talking about, so in 2003 we started at 130, now we are talking about 18 nanometer. And pretty soon, 10 nanometer will come from TSMC. So scaling, it is observed that from generation to generation of Intel microprocessor and other ICs, technology shrank by 0.7 per generation. That means when in one generation, if it was 100 nanometer, the next generation it was 100 by 0.7, 70 nanometers. So it went down on average by a factor of 0.7 per generation. During this time, the cost of implementing each logic function decreased by a factor of 2. Otherwise, if the cost of implementing each function remains same, when you are cramming millions and millions of transistors to implement more function, then your cost per IC also would increase linearly with the number of functions you are implementing per IC. So it has to go down, cost per function. Function means a logic function, producing binary ones and zeros. Those are the logic functions, right? Functions, from logical point of view, you have to produce a stream of ones and a stream of zeros. If your cost per logic 1, if your cost per logic 0 remains same, you move from several thousand to several hundred thousand to several hundred million to billion. If the cost per logic bit remains same, nobody would be afford any computing or cell phone, right? So it has to go down. So per transistor cost, per logic function cost must decrease, and it decreased by a factor of 2. That's why one of the popular example of Bill Gates, if automotive industry could follow a fraction of an improvement or growth like an IC industry, we will be driving 1,000 mile per gallon car today, right? But this is remarkable only in IC industry. So once again, as I mentioned, now earlier you mentioned the gate length, right? Gate length is the technology size, but ideally, NMOS and PMOS, ideally the channel length, insulation oxide length, and gate length should be exactly equal. But practically, this body layer is formed first. And the source and drain region, practically, we will never be able to produce a perfectly rectangular source or rectangular body. It will have kind of a distorted edge. So the channel length from the top to the bottom will not remain same. So it is a standard to basically assume that the channel length would be the length of the region right at the top surface of the transistor. That is the channel length L, that is the technology size. And then once the body of the transistor is formed, insulation gate oxide layer is deposited as a liquid on top in a process called chemical vapor deposition. So once you are depositing a liquefied gas on top, it will never stop at here, it will spread to the left and to the right a little bit. So the insulation oxide length will be always slightly longer than gate length or the channel length. And then once you are done with gate oxide layer, on top of that you will be depositing gate metal layer or gate conducting layer. That is also done by a chemical vapor deposition, liquefied gas of polycrystalline silicon or whatever. When you deposit, it will also spread beyond this edge and this edge, thereby making the gate length in practical transistor slightly larger than the channel length. So that's why when it comes to technology size or transistor size definition, we will only take this length, the distance from source to the drain at the top surface of the body, right beneath the gate layer. Not this size, because this, as you see, is distorted. So this is more of a practical cross section of an NMOS transistor or PMOS transistor, whatever. So that is the end of our part 2. So now see what we have in part 3. Any question up to this time? Either whatever I am saying is not making any sense, or if you guys understand everything.
I have a question. Like
Yeah.
you're saying this size, it's becoming smaller and smaller.
Yes.
So 1 year ago, I read an article that IBM has made a chipset that costs 2 nanometer,
Yeah.
50 billion transistors inside.
Yeah.
And
So 18 nanometer is in commercial production. In lab setting. So three company invested heavily on 10 nanometer. 10 nanometer, they started investing about 12 years ago, 15 years ago on 10 nanometer. It was Intel, Global Foundry, and TSMC, Taiwan. They spent about $15 billion to pioneer 10 nanometer. But before Intel and Global Foundry could commercialize and pioneer 10 nanometer, they already published the model, commercialized model. So after spending $15 billion almost 10 years, Global Foundry laid off. They had to lay off everyone they hired for 10 nanometer projects. And one of my former PhD students also got laid off in the same batch. But he immediately got a job in Intel. So then, Global Foundry and Intel later decided that, well, TSMC already took the leads in 10 nanometer, so they started on 7 nanometer. Simultaneously, there are other different variations of CMOS technology are being explored. So now they are trying to, IBM is a big player, they are now trying to 5 nanometer and 2 nanometer. And IBM and all those big companies, they are now exploring, because pretty soon either Intel or Global Foundry probably will publish everything, all the model, simulation model and everything, and basically they will start licensing this model in the future. So probably TSMC will not spend any money here, it will probably jump here, right? So that's the beauty of the research. So it is continuously jumping, and at one point they're saying that below 1 nanometer, can you scale it down further?
That's the question I was going to ask. And also, how does it work when there is too small? How does the electron move past
So
it?
that's basically when you are becoming 1 nanometer long, the question is, within that 1 nanometer, how many silicon atoms can stay to reasonably construct a stable, reliable channel? That's basically they are now getting into. So beyond that, so everybody is predicting that probably next 20, 30 years, CMOS technology, planar MOSFET already reached its limitation. The CMOS technology will hit the dead end.
Okay.
Then something else will come over. But in this, so the advanced VLSI design, so we will have first 3 lectures on next generation device. So I don't want to complicate in this introductory lecture, but that is a valid question, very good observation. Below 1 nanometer, probably this MOSFET will not physically exist as it is, because it will become very unreliable. But in this part of the lecture, I want to just quickly show you the manufacturing process or steps of IC before we move to detailed analysis of MOSFET. So in IC industry, so Intel or NVIDIA or AMD, they design the IC, but somebody else must manufacture that IC. TSMC is the leading manufacturer. They manufacture more than 50% of all the global ICs single-handedly. So where the process starts? The process starts by separation of silicon from what? Sand. Sand is silicon dioxide. By separating oxygen from silicon dioxide, sand, silica, we got silicon. Silicon, after purification, it comes in a cylindrical form. It's like a big salami, like a hot dog form, a salami form. Those who are from East Asia, if you are visited East Asia, you know that over there in East Asia, they don't. Hot dog is not very popular. It's like big salami. They slice it and they make burger in front of you, right? So it comes as a big salami form, as a cylindrical form of silicon material, and average diameter is 12 inch. So the first step of IC manufacturing is to slice those cylindrical silicon, and each slice becomes a circular disc of minimum 4 to maximum 12 inch in diameter. This circular disc of silicon, which is several millimeter thick, about 10 to 30 centimeter in diameter, that is called a wafer. So from cylindrical silicon, purified silicon, we get, by slicing it, we get a wafer. On the wafer, integrated circuits are printed exactly the way old days photography, the negative based photography printed on a paper by exposing it to the light and different shades of negatives, right? You print it exactly using a series of negatives, like for original old days negatives. In IC industry, it is called mask. Masks are nothing but some patterned, transparent or non-transparent polymer plate, like photo negative. Have you seen those negatives with all pictures? So when we print, we print using a series of masks the IC patterns on the wafer. On the wafer, we divide the wafer into small rectangular region. On each rectangular block, we print one IC. And when we cut it, that rectangular block is called a chip. A piece of the wafer. The wafer is a disc shape of silicon. After printing all the circuits on the wafer, on each rectangular block, one IC, each one probably is one microprocessor. This is an AMD, actual AMD wafer. So each rectangular block is AMD Athlon microprocessor. So this is the wafer. So cylindrical silicon wafer, and then finally printed wafer. Once we cut this wafer into small rectangular block containing one IC, each one of them is known as a die, a single die, also known as a chip. Right? So a chip or a die is a rectangular block on a wafer. And a wafer will contain hundreds, maybe dozens of ICs printed on it, and it is started with this circular disc of silicon. It goes through many numerous processes, and that process from here to here, it is one of the most complicated and expensive manufacturing process you can imagine. That's why only 10 IC manufacturers, they manufacture 99.99% of ICs globally. The problem is 6 of them are in either Taiwan or South Korea, and 2 are in China. America has only 2, Intel and Global Foundry. But Global Foundry was an IBM spin-off. It was sold to Prince of Abu Dhabi in 2006 or 7. So Global Foundry, it is still in New York, but it has been privately owned by the King family of UAE, but under the pressure from US government, about 7 years ago, they made it a public limited company. Now it is listed in New York Stock Exchange. But still the controlling share is owned by the Abu Dhabi King family, and it is the second largest foundry in the land of the United States after Intel. And now they are investing heavily in Singapore. By treaty with the US government, they cannot have any plant in China or any country that is not friendly to the United States. That's why they're expanding their facility only for commercial ICs in Singapore, but all the security restricted ICs for US government and other companies, according to the contract, it has to be manufactured in New York. So Global Foundry New York is one of the big employer of IC manufacturing. Yes.
And I guess the closest phrase I could use to describe them is the printing presses. But what are those tools called that they use to do that lithography?
So the master machine, now again, the master machine for IC industry are made by few companies, including Samsung, and one is called Cobalt, that is headquartered in Aurora, Illinois. So, and some of the master machines are customized, patented by this TSMC, ST Hynix, Samsung, and UTC, United Technology Corporation, owned by China. So there are 10, just Google search, there are 10 top IC manufacturers or semiconductor manufacturers. Each one of them, they have their proprietary machines. Some of the accessories are supplied by some of the supporting company. It takes hundreds of billions of dollars investment over the course of many decades to pioneer this technology. That's why it is so expensive and so unique technology. Nobody would share the secret. That's why United States became the leader in IC patent, IC design, but somebody had to manufacture it. They thought that it will be very cheaper, easy to be manufactured from Asian countries. So they relied on those. But now, remember 3 years ago, across the United States, the car prices went up. All of a sudden, there was a shortage of new cars because GM, Ford, Chrysler, they had hundreds of thousands of cars ready, but they couldn't finish the dashboard because inside the dashboard you have minimum 10 to 20 microprocessors to run all the touch screen and everything, right? Yes.
What about Texas Instruments?
Eh?
What about Texas
The
Instruments?
problem is Texas Instruments, NVIDIA, AMD, Qualcomm, Cisco. Everybody has hundreds of IC products, but they all send it to TSMC. Even my PhD student Maruf, who is now working with Qualcomm for the last 1 year, he cannot submit his PhD thesis because part of his PhD thesis is to have an IC manufacturer. He has done all the simulation and everything. Because his research is outcome, he claimed that will result in an IC, final product IC. So for the last 1 year, he is still waiting for his IC to come back from Taiwan. For all the academic IC manufacturing is so, any IC manufacturing is expensive. But we as the faculty and student, we don't have enough money to have a prototype IC manufacturer. So there is an organization called MOSIS. MOSIS is a non-profit organization operated by USC, University of Southern California. They are the host of MOSIS. So anyone, if you are doing any research that needs an IC manufacturing, you have to do some paperwork, get it signed by me, your advisor or any advisor, signed by our official research service that you are not going to use it for any commercial purpose. It is purely for academic purpose. MOSIS will accept this, but MOSIS is an organization run by USC. It doesn't have manufacturing. TSMC, being the largest manufacturing company in the world, they do some benevolent work. And one of the benevolent work is doing free manufacturing for academic ICs. So MOSIS gets all of his ICs manufactured by TSMC. So my student sent his design to MOSIS in 2022. There is a 3-year long queue. Because everyone from all over the world, at least all over United States and Canada, they are sending it to MOSIS, and MOSIS is waiting in TSMC queue. Probably they had one separate small setup for academic manufacturing.
So that sounds like a whole lot of tuition. That sounds like a whole lot of tuition. Is he stuck taking classes for those 3 years?
No, good thing is because he has a full-time 6-figure job in Qualcomm R&D. So because he completed his thesis as well as research, all 36 credit. So university allows this type of student to maintain continuous enrollment with 1 credit thesis, and you can continue it year by year extension with the permission of graduates. So all he is spending just base rate for 1 credit, 1 in fall, 1 in spring, nothing required in the summer, and in the state rate. Sometimes I am paying, sometimes he is paying, just $500-600 every year. So now let us look at the IC inside. So when ICs or dies are manufactured, cut into smaller rectangle, each die is placed inside an IC package to protect it from environment, moisture, and other thing. So IC package also went through revolution and evolution over the last 4 or 5 decades. These are the many different types of IC package. We'll talk about it in a separate lecture. This is what a three-dimensional view of an actual MOSFET. It has length, width, and depth. This is a microphotograph of an actual die after manufacture. Different color coding in the microphotograph means different layers. Sometimes it's insulation layer, sometimes metallic interconnect layer, sometimes transistor layer. But if we deep dive into any of those points into this die, this is what we see inside an IC. If we use a very, very high power, high resolution electron microscope inside this die, this is what we see. This is an actual microphotograph of an Intel processor. And as you can see here, it says metal 4, it says metal 3, it says metal 2, it says metal 1. This one is going this direction, this one is going this direction, this one is going this direction, and there are some vertical line going down. This is how interconnect lines are actually organized and connected with the transistor inside an IC. So why there are many layers of metal? Metal means conductor. So these are interconnected wire connecting millions of transistors together to form the microprocessor circuit. If it is a Pentium 4 processor, we're talking about 55 million transistors. So 55 million transistors sitting on a layer of silicon side by side. You have to connect them together in many different patterns to form the circuit. So to connect 55 million transistors, if you put just one layer of interconnect line, metal layer, on top of the silicon surface, you will not have enough wire to connect them. So that's why in actual IC, there will be multiple layers of interconnect line placed on top of each other. And for making connections easy, if you have more than one layer of interconnecting wire, it is standard practice to place them parallel to, let's say this is my IC body. So they must be parallel to the IC body horizontally, but I should put one layer in this direction, one layer in this direction, so that I have some intermediate gap to run the connection vertically from the transistor to the wire you are trying to connect it to, right? So it's a standard practice inside IC. If it is the body or the base layer of the transistor, if metal 1 runs in this direction, metal 2 will run in this direction. Metal 1 means layer 1 interconnect line. Metal 2 means layer 2. Metal 3 will run in this direction. Metal 4 will run in this direction. In alternate direction, left and right, left and right. But they are all in horizontally parallel to the body. So in current generation 18 nanometer technology, we need so many transistors to be connected. We need up to 11 layers of metal lines, hundreds and thousands of lines running in this direction. So, and then we need to bring vertical connection from the transistor to connect it to different line in different layer. So these vertical connections are known as vias. These vertical connections are known as vias. And these horizontal lines, metallic lines, they are called interconnecting wires. Those are metallic wires to connect transistors together to form the circuit. So this is what actually we see inside IC. Now, I am going to now briefly discuss different design steps. You as the IC designer, let's say you get a job in Intel, you are working in a large team to implement a new design for a new microprocessor. So you have to know what are the different steps, design steps, what are the different groups of engineers and scientists you are going to work with, and you as a VLSI expert, where you stand in this big picture. So, and how it is related to the courses you are taking. So, like, let's say you are given the task to design a new campus for UMKC. Somewhere in Independence, they gave you a 100-acre land. First, the state governor and our chancellor, they will not focus on the detail. They will say that this is the new campus, a new IC system. It should have 10 student academic building, 5 labs building, 2 dormitories, 1 canteen building, 1 common facility. They will basically plan what exactly, it's a medical school extension, engineering school extension, or all school extension. What exactly we are trying to implement. They will look at the broader picture, bigger picture. So the system designer in Intel, they will think that, well, I want to have a new microprocessor with currently it's a 256-bit architecture. I want to implement a 512-bit architecture microprocessor with 2 terabytes of built-in RAM with 16 core. So they will think about the system designer, and they do not need to know all the internal details about different technologies. Then, once the system level, the state governor and our chancellor, they do not need to know all the details within the campus. They decide that we are building a new campus. That's it. So the system designer, but the next level is the module designer. The module designer called architect, computer architect. They have to know, well, this 100-acre land, how we program it, or this 9 square centimeter chip, how we are going to plan it, how many different building blocks, that means how many different buildings, roadways, alleys, parking will be in the campus, in the chip. That's where the computer architect, people with computer architecture background, mostly from CS and electrical engineering, computer engineering background, they will be here. The next step is for each of these building blocks. Now I have to know, is it a memory block? Is it a DSP block? It is an input-output block? It is a microprocessing block? Or it is something else, power regulation block? In each block, what type of logic circuit I need? Do I need MOSFET, or if a power block, we need probably junction FET, JFET, power electronic device, right? So inside each block, each module, we need to determine what type of logic circuit functions we need to implement. Once we do that, so that is at the logic level design, that is called logic synthesis. There is another huge group. They will decide, okay, it is better to use 4 input gates versus 6 input gate or 2 input gate. They will make all those decisions. It's called logic synthesis. Then, when they are done with logic circuit design, functional diagram, now each of these logic circuit, what type of circuit technology are we going to use? NMOS only, PMOS only, CMOS, or something else? If it is CMOS, what are the parameters, size, number of line layers, how many wires, how many horizontal layer lines we need, right? How many transistors we need to implement all these circuits? Can I minimize those circuit size to be able to implement it with lower number of transistors? How can I implement more functions with less transistors? So those type of design will be handled by circuit design. But then the next level is, no matter what circuit you are designing, it has to be implemented by certain technology generation. 18 nanometer, 10 nanometer, 5 nanometer, that will be decided by your device designer or company. They already decided that we are going to implement this new system with 10 nanometer. So how can I basically accommodate my design to be compatible to a 10 nanometer device? So there is the device engineers. VLSI design is mainly here, but you have to have a very clear understanding how those logic functions and designer work, and you have to have a clear understanding how the device you are going to use You don't need to be a detailed device physicist, but you have to have a basic understanding how a 10 nanometer transistor is different from an 18 nanometer transistor, right? How can you make it comparable to this, right? So like for example, today when I was setting our new lab, there was a black bench in Cluster Center. I wanted to take it to my new lab, but the size of the table is much wider than this door. So now I called facilities, can you help me? They said, well, we can do it, but you have to pay us $600 to take it apart because it's a very expensive lab bench and put it back to your lab. So you need to know whether the circuit you are designing or the device you are asked to use is comparable to your circuit. So you have to have a knowledge about device, you have to knowledge about the logic gates, but you have to have an expert in circuit design. That's where VLSI design stands. Circuit with an overlap with logic gate level design, with an overlap with device level design. So this course will be basically handling here. Interestingly, different types of course you will be taking will actually fall under different stages. So if you want to take a physics course on semiconductor device or an electrical circuit course on semiconductor device, then you will be learning more in detail about the transistor. So we will end with this slide because you are taking introduction to VLSI design. So you have to know what the term means. The term is very large scale integration, VLSI. So you as the VLSI designer, this course will provide you the foundation, or through the techniques we are going to learn in this course, will tell you how to implement a VLSI circuit, a circuit that contains over several million transistors to several billion transistors per IC. Yes.
So as we talked about there was a PhD student who was actually creating a PC, I would say a chip,
Yeah.
and it's like coming in a year. So is it like the college can file kind of patent towards that thing if it is unique and if it is like working research?
So yes. So he actually submitted a patent on his design, but it was rejected because patent is a very lengthy process. Initially, we got a provisional patent, but the patent examiner in Washington, D.C., they are very smart, they are very rigorous. So they found out that somebody, probably in South Korea or Japan, came up with a way